So welcome guys. So in last lecture we discussed about the derivation part of the steady flow energy equation and the assumptions made while deriving the steady flow energy equation. So in this lecture we are going to discuss about a problem in steady flow energy equation, and this is a typical problem. Especially we can understand various steady flow devices, real-time steady flow devices, and you'll get much understanding about how to solve a problem in most of the steady flow energy devices. So air at a temperature of 15 degrees Celsius passes through a heat exchanger. You know that heat exchanger is an open system. So heat exchanger is an open system. So steady flow energy equation can be applied to the system, and is 15 degrees Celsius. So T1 is 15 degrees Celsius, and the heat exchanger at a velocity of 30 meter per second. So C1, capital C1, velocity at entry is 30 meter per second, where its temperature is raised to 800 degrees Celsius. And we know that the objective of a heat exchanger to raise the temperature of the fluid, and the temperature is now raised to 800 degrees Celsius. So 800 degrees Celsius is the temperature we've got after adding heat to the system. So this T2 is 800 degrees Celsius. It then enters to a turbine with the same velocity of 30 meter per second. So C2 again, C2 is 30 meter per second. So here the kinetic energy change is negligible because both entry and exit is same, and expands until the temperature falls to 650 degrees Celsius. So T3 is 650 degrees Celsius, and with the help of diagram you can clearly understand here. Now you can see here it's a heat exchanger. Entry the temperature 15 degrees Celsius, velocity is 30, and the objective of heat exchanger is to add heat to the system. So we will be adding heat. Heat is added to the system, and at exit the temperature is 800. We have added heat, so the fluid temperature is raised. Velocity is same as entry. Now this is allowed to a turbine. Okay, so it's allowed to a turbine, and the turbine exit temperature is 650 degrees Celsius, and the velocity is 60 meter per second. So there is a gain in kinetic energy too. So now this is allowed to a nozzle where the temperature is dropped again to 500 degrees Celsius. Now the objective of a nozzle is to raise its velocity. So we have to identify what will be the velocity at exit of nozzle. So this is given in the problem, and the airflow rate is 2 kg per second. Calculate the rate of heat transfer in heat exchanger, the power output of the turbine assuming no heat loss. So it's an adiabatic expansion process. The velocity at exit from the nozzle assuming no heat loss. So it's an adiabatic expansion again in nozzle. Take enthalpy of air as H is equal to CPT. So it's CPT. So we have two expressions for enthalpy. One is H is equal to U plus PV, and H is equal to CPT. In these cases, we can use H is equal to CPT easily. So Cp is specific heat at constant pressure, and the value is 1.005 kilojoule per kg Kelvin, and T should be in degrees Celsius. They have told that while calculating enthalpy, enthalpy of state 1 can be simply calculated by H1 is equal to Cp times of T1. T1 is temperature at entry. That while multiplying the temperature with Cp, the temperature should be in degrees Celsius. So now let's move on to the solution part. So now I have given the flow chart of the given question 2, so you can clearly understand by seeing this flow chart. Now for solution, it's very simple. We have three series of steady flow systems. So we'll take one by one for an instant, and we apply steady flow energy equation, and we'll get the answer for the required thing. So first one is heat exchanger. So we need to find Q1 to 2, and we know enthalpy of air is HPPT. So we get H1 as the product of this, and so keep in mind your temperature should be in degrees Celsius. So here also degrees Celsius, we got the enthalpy value, and H4, H3 also we have got. Now we know the steady flow energy equation formula. So it is m times of Gz1 by 1000 plus C1 square by 2000 plus H1. The thing is, if you remember the last expression I've written here, the unit for enthalpy is kilojoule per kg. Since your Cp value is kilojoule per kg Kelvin, so unit for enthalpy is kilojoule per kg. But when we get Gz1, instead of Gz1 by 1000, if we substitute only Gz, and C1 square by 2000, when we substitute only C1 square by 2, then this equation will be in joule per kg. So when you are substituting H1 in kilojoule per kg, if you are not writing 2000 and 1000 in the denominator here, then this will be in joule per kg. and this equation is not dimensionally homogeneous. So make it dimensionally homogeneous. We are substituting 2000 and 1000 here. And if you feel that this is difficult, then you just convert the unit of enthalpy as joule per kg. But here we are substituting in kilojoule per kg, therefore it is 2000 and 1000 here. Substitute it and you'll get the answer for the heat transfer. You can clearly understand. If you want to understand, you can pause the video and you can go through the steps. You can clearly understand it. So next one is steady difference equation for turbine. So turbine, there is no heat transfer, they told, and the potential change is zero. There is some gain in kinetic energy. So the C2 is not equal to C3. So if you substitute these three conditions, we'll get the value for W223. And the third one is a nozzle. So nozzle, the potential change is neglected. There's no heat transfer, there's no work transfer. So the final expression for the C2 or C4 is equal to this value for C4 is 52.358 meter per second. So it's very easy to understand. So kindly you can go through this, and I will also give this PDF file to you can go through. We can work out a similar problem to understand it in better case. Thank you.